So now I would like to welcome my colleague from Scientific IT Services, Dr. Franziska Oschmann. She is currently a data scientist at the Scientific IT Services of ETH Zurich. Franziska is closely collaborating with researchers at ETH to implement machine learning solutions for their data processing and analysis. Her projects range on a wide variety of fields, ranging from computer vision to NLP to analysis of omics data. Franziska has a background in computational neuroscience and obtained her PhD in that field from Technical University Bern in 2018. Welcome, Franziska.
Good. Thank you very much for that nice introduction. So as Tarun said, I'm quite happy to introduce today how SIS is supporting AI in research. And first, I would like to okay, that's how it's working. Okay. So first, I would like to start with a short introduction of what SIS is. So SIS are the scientific IT services of ETH, and we are a pool of experts of 45 members, and we are providing scientific IT support for ETH researchers. And so the fields we are working in is quite broad. So we have people working on scientific computing and data science. So that is the field where I'm working in. Those people have various backgrounds, mostly have a research background, so did their PhD in various fields. There are also scientific software developers with a background in computer science or industry experience, but there's also system administration and DevOps. So those people are running the HPC infrastructure of ETH and also research IT platforms. And so the main areas where we see our tasks or where we are working is first to enable research, and the second one is to improve the efficiency. And the enable research part means that, so let's say there are researchers from life sciences which don't have a lot of expertise in machine learning, for example, but they need machine learning to analyze their data. And without having that knowledge, they basically can't reach the goal. They can't analyze their data. And by getting support from us, they can actually get the results they need and we enable their research. Second one is to improve the efficiency. That can mean various things, like, for example, since we run the ETH cluster, people can run their computations on the ETH cluster, and by that we improve the efficiency of their research. But also, for example, there's the scientific software development, so by code improvement, we can also improve the efficiency. The working model is quite similar to what Simon just told us. So we have different types of contracts, so people actually have to pay so that they're getting our support. So one model is that there's a few days of full-time support, so depending on the project, people get 5 to 10 days, for example, of full-time support. But what is more common is that there's, like for 1 or several years, a part-time support ranging between 20 and 50%. That's quite common. So that means one of the SIS members is working for 1 or several days per week with that specific research group and providing the support. And so I would like to show this figure. I mean, it's also highlighting the different areas where SIS is working, but I would like to highlight those which I didn't mention so far. So one is the scientific visualization. So it is also part of the computer scientific computing service we are providing, and then also we are doing a lot of consulting and training. So there are also, for example, machine learning courses, Python, code optimization courses, which are also offered by us for PhD students and postdocs. And now I would like to highlight one specific project I've been working on during the last 2.5 years, which is in collaboration with Professor Ackermann from ETH Zurich, and it's about the segmentation and tracking of cells growing in microfluidic devices. And so first I would like to explain the data a little bit. So what we see here is a video of these cells which are growing in these chambers. So we see these 3 different chambers here, which are close to 3 sides, and then there's one side open, and we have this channel down here, and there's a liquid flowing through the channel with nutritions, providing the nutritions to the different chambers. We can also go back again so that we can have a look again. Like this. And what is also important to note here is that so we have per chamber, we have different cell types. So the researchers are interested in the interaction between different cell populations. And so for that reason, so what we're seeing here are phase contrast images. So there's a specific type of images. But they're looking at different cell types at the same time. They use different fluorescence channels to analyze the cell type separately. That is also a challenge in the whole segmentation and tracking analysis. Good. So in the end, what the researchers would like to do is to quantify the population growth and dynamics over time. And what they need for that is things like the number of cells, position of cells, also relationship between cells, so there's also cell division happening, so that means they want to know what is a mother cell, what is a daughter cell, and when a cell split is happening. They're also interested in the movement of cells, or for example, the interaction between cell populations. So because there are also population dynamics happening, so depending on the location where a specific cell is, so they're also interested in that. So in the end, what the researchers need to get from their raw image stack to the growth rates of single cells and populations is an image analysis pipeline, which is covering different aspects like further pre-processing, which can mean various things like cropping the images, deconvolution. There are various things which can be done. But I think one of the most important steps is cell segmentation, as also Simon said before. I think that is for every image analysis project one of the main steps. And then also based on the cell segmentation, the cell tracking, so that you can track the single cells over time. And then based on all the results you achieved by cell segmentation and cell tracking, also the post-processing, so that you can actually look at these population dynamics. The group used state-of-the-art tools before, also mentioned by Simon before, like ImageJ, Elastic, SuperSegger. But the problem was that all the tools they tried, these methods didn't work out properly for their data sets. So I think one of the main challenges was for the different fluorescence channels, the segmentation didn't work out properly, and then there are also cells in close neighborhood to each other, almost touching. That is a great challenge for the segmentation. Another problem is that within the group there is no software development or machine learning expertise. That means they highly rely on those tools to work properly for them so that they generate in the end their results. Otherwise, they cannot process the data and they just have the image data but not really the processed results. And that is a dead end in the end. So in the end, the whole data analysis part in that group was a bottleneck for the research work. And that was the point where they contacted us to get support and so that we together work on one image analysis pipeline. And so as I said, we started that project 2.5 years ago. And so one part of this whole image analysis pipeline I would like to highlight here is the data set generation. So I will further on also tell a bit about how we did the data segmentation and tracking, the cell segmentation, cell tracking. But one important step is also to generate data sets to really train the models, because you always need a good training set to train and validate models, and these segmentations is a tedious task, so it's a quite time-consuming task to generate those data sets, and for that reason I wanted to put some effort into what is the best way to really generate these data sets with the least minimal effort, manual effort. So the good thing about the images we've seen before is that they are quite large. So we have 500 times 500 pixels, and each cell is only 30 times 30 pixels large. So that means per image we have a lot of different cells, and we can just easily separate one larger image into smaller patches, and by that retrieve a lot of training data. So in the end, what was done here is, so we start from the original image. We divide it into smaller patches. These patches are divided into train and test based on their cell coverage, and then based on these smaller patches, there's a random patch generation, and then in the end, there's data augmentation. So in the end, what we could do here is, just based on one single image, we could generate around 8,000 training images, which is basically enough to train a neural network for such a task. So, and then it was also mentioned before, or already mentioned before, but so the method which was used for the segmentation, I mean, there was a lot of back and forth between the researchers and SIS. So they were, or in the beginning, they wanted to use like traditional methods. We tried that, didn't work out properly, and then in the end, we chose to use the UNet, which is, I think, the state-of-the-art segmentation network. I don't want to go too much into detail here how the network is working, but maybe just so that you get a rough idea of how it's working. So we have the network structure here, and as an input there is the raw image, and you get out the segmentation image. And what is quite special about this architecture is that you have these downstream branch here and the upstream branch here, and the downstream branch is learning the what information, so how is a cell looking like, and the upstream branch is learning the where information, so actually where a specific cell is, and then there's also this information fed from one branch into the other. So this network is the gold standard for doing segmentations with neural networks. It has a lot of citations and is the winner for several image segmentation competitions. So it's, I think, I think the choice for doing segmentations with neural networks. And as I said, like the approach which worked best for us. Next, I would like to show you one example of how the segmentation really looks like and how well it worked. So on the left, you see the cropped image. So in the end, the researchers are interested in the single chambers, not the whole image I showed you in the beginning, but just the single chambers. So that is just for one cell type. Before I showed you two different cell types, that is just for one cell type. You see that it's there's a lot of movement happening, somehow a downstream movement. And now we can also have a look at the corresponding segmentation image. And compared to the methods which have been used before, that is a huge increase of the quality of the segmentation images. And during the training, we could achieve accuracy of around 98, 99% for the segmentation images. So it means that step with using the UNet is, I think, a huge advantage for the group and helped them a lot in their whole image analysis and image processing. What is a little bit more complicated is the cell tracking. So there's one approach also using the UNet, and I think there are actually several approaches also using the UNet, but there's not this one approach with neural networks what you can use for tracking. That UNet is a little bit adapted to the needs of the tracking, so you don't have only one input, so you don't have only the raw image you put in and the segmentation image you get out. So actually what you have here is on the left the raw image of the previous time frame, the seed cell you want to track, the raw image of the current time frame, and then also the segmentation of the current time frame. And then what you get out is the mother cell, and in case there was a cell split, also the daughter cell. And so as I said, there are many different approaches out there, and I think it's not like we also have to investigate a little bit more if it really makes sense to use one approach or maybe also others. But so since UNets has already been used before and that approach sounds quite promising, I started with that one, and I would also like to show you a result for that. So what we see here is the tracking over time of one specific cell, what you see here, up here, so what is highlighted in red. And for this specific case, I used a pre-trained network. So, I mean, for segmentations already, it's quite time-consuming to generate these training data sets. For tracking, it's even more time-consuming. So the idea was before generating all these data sets, what we do is we use pre-trained networks, have a look at how well it works for our data sets, and then after we evaluated the results, maybe do a fine-tuning of the networks based on improved data sets. And so I think actually the first results don't look too bad. So you see that there's the cell moving, there's also cell split, which is captured by the network. Then somehow something is happening here, kind of a shift. So the cell somehow gets lost a little bit, but then in the end it's working again, so we can have a look at it again. So you see, I think the beginning looks quite good, but then at some point it jumps a little bit, so but then it's fine again. So I think, but that is already a good start for doing corrections of data sets and then using these corrected data sets for fine-tuning of the network. I think that's already a good starting point here. Good. So what I've showed you so far is this image analysis pipeline I developed for this specific research group. So including the pre-processing, the segmentation, and the tracking. And now, since the approaches are working quite well, there's an increasing interest from collaboration partners from that specific group who would also like to use that pipeline. But of course, this upscaling is also coming with specific needs, and also some adaptations are needed for that pipeline to make it available for that upscaling. So one is definitely on the neural network part. So if we have more people who want to use the pipeline, there are also different data sets, different experimental setups which should be also captured by that specific pipeline. So I think definitely the cycle gun is something maybe you should look at to make the neural networks more general applicable for different data sets. But then there are also like requirements coming from different perspectives or from different sides. So one is, for example, a GUI for which allows manual correction of the segmentation and of the tracking. Of course, that also is, I think, a quite good idea of using these improved data sets for fine-tuning of the models again. Then when we talk about a lot of people using that pipeline, also workflow managers, I think is a good idea. It was also required from these new stakeholders coming into the project, because one thing is that they could enable modular usage of the pipeline instead, in case you want to start with one step in the beginning, let's say the segmentation, and you want to later on do the tracking, or you want to use your own algorithm for tracking, you just want to plug in. I think there are different possibilities. Also, storage of metadata is now quite important, since you just want to keep track of which parameters, for example, you used for your data analysis. And then also, last but not least, HPC. So if you want to run now a lot of data set at the same time, if you want to process it, then running it on a cluster also makes sense. So far, the pipeline is just running on local computers of the researchers. And so that brings me back to the different areas of SIS I was talking about in the beginning, because so far the pipeline was just a machine learning pipeline. So I developed it on my own. It was mostly machine learning approaches for solving these image analysis tasks. But now there are also other tasks coming in, like the implementation of a GUI, workflow managers, HPC, and so on. And now the nice thing is that SIS is providing all these solutions. So I can go back to my colleagues, I can pull in other experts, and we can provide one solution not only for the data science machine learning part, but also for the HPC, software development, and scientific computing part. And we can provide one solution for everyone, for the research group. Good. So I would like to close with a few thoughts about the benefits and challenges of this collaboration model. And as I said before, so one benefit is definitely that we have this pool of experts which can work together on one solution. And by that, so I think it's quite important here that the solution is just coming from one service provider. And that also makes it, so this collaboration model makes it easy for the researchers to access knowledge which they would not have otherwise. So like, for example, machine learning expertise. And then also, I think that's not special to SIS, but in general, what we are doing quite often is that there's a continuous exchange between research and SIS members. So usually there's a back and forth between us and the researchers to really find the best solution. So like, for example, for the segmentation approach. But of course, there are also a lot of challenges and risks. Like, for example, one is to find a common language. So between the IT and biology, it's always a problem to really find a common language. Expectation management, I think we also heard about that before. So we cannot perform miracles with neural networks. So if you cannot see by human eye how cells are looking like in the image, then probably the neural network can't do it either. And then also one thing is that doesn't apply to this specific project, but to other projects, not every field or not every problem is suitable for the application of machine learning. So I think for images, it's quite easy because it's quite easy to understand what should be done, but I think for other areas, it's a little bit more complicated. And yeah, with that, I would like to finish, and yeah, we'll be happy to answer questions.
Thanks a lot, Franziska, for this very nice talk and giving a very nice overview of how SIS works. It's always a pleasure to hear it. So are there any questions from the audience? I see Simon is raising his hand.
All right, thank you. Yeah, very nice overview indeed. Let's start with one question. The last thing you mentioned made me think, why are you even using a UNet or machine learning at all for tracking? Because, let me just explain why I ask. It looks like you have a very small delta t, meaning the center of mass of a cell always stays within the boundary of the cell in the next time frame. So that's like, again, almost blindfolded, you can track that. Of course, divisions is a special case, but still not hard to code. So
yes.
Why machine learning?
So the thing is, so the UNet for tracking was trained on a data set, I think, where they used like delta t of 5 minutes, I think. But usually they have one of 10 minutes, and they also want to account for that. So the idea was, okay, so since the network's already trained for 5 minutes, we will also use the data set for 5 minutes, see how well it works, and then maybe from that go further and then also use the tracking network for other data sets. But in the end, you are right. So in this case, you could argue that probably another approach could also work. But I think that's like the easiest case we are working with.
Do we have other questions?
So I just simplify things, but apparently the problem, it looks like the conceptual problem is like simple, right? You got a cell and you want to like look when it moves. In that case, you might argue that you don't really need to understand a lot of the biology and why cell moves and in what direction they go and all these kind of things. Is that really the case, or do you need to is it helpful for you to know much more about why this cell moves and in which directions and these kind of things?
So I wouldn't say that why it moves is important, but where it moves, definitely yes. Because if you train the neural network and you already know that probably a cell will move in that direction, you can already integrate that into your training process. By that improve the prediction of the network. But the what, for the moment, I would say it's not that important. But it depends on the analysis you want to do in the end.
Thank you.
You mean you would like to apply a more statistical approach?
No, I'm not talking about you wouldn't use the... No, it's just very often it takes a lot of time to understand what is actually the process and also to make sure that what they ask you to do is the right thing to do. In this case, apparently at least, it looks like very simple. You get a cell and you follow it. But I was wondering whether, knowing why cell moves and how they move and all this kind of information is bringing any value to how you then model this process, or whether in these cases it is as it looks like, it's just simple and you don't need to know much more than a cell is moving and I follow it. That was my point. I'm really curious, I was really wondering whether this is, you all need all this additional information or not.
So yeah, for the moment not, but I think definitely the direction will be important at some point, yes.
We have another raised hand at the back.
Thank you for the nice talk. I had a question on the tracking algorithm. Do you need the frames to be very close in time, such that there is some overlap between the cell? Or could it track the cell even if it moved by some large amount? Could it recognize, does it only use, I would say, some kind of optical flow or some kind of overlap between the frames, or can it detect some unique features of a cell to do some kind of face recognition of the cell to recognize it, even if it's super far away from the previous frame?
I think there are definitely limitations to that. So since, you saw the cells, I wouldn't say that there's a unique shape for every cell. So they look quite similar. So definitely, I would guess that you need some kind of overlap. and definitely if you have 1 hour between the different time frames and the cell moved completely somewhere else, then I think you won't get a good result. But we didn't check yet how much overlap you need. But as I said, so for the moment we use a pre-trained network for one specific delta t, and we have to see how much we can push the delta t to still get good results. But yeah, we're still working on it.
Do we have another question? Okay.
Just following up on some of the previous question, I was wondering, because you were pointing out that sometimes the cell was being missed or disappeared, and there were several questions about, like, using machine learning versus using something which is tracking methods. I mean, have you considered the possibility of requiring from the UNet to actually produce some form of optical flow, which could perhaps go further than what, sort of a simple optical flow would do? Because this would have the advantage that if you ask the UNet to produce the optical flow, that maybe it would be more difficult to lose cells. I don't know.
No, actually not. I mean, so I was thinking about which different directions, or in which different direction we have to go, and or we could go, and if really a unit is necessary for doing the tracking, because I mean, depending on the data set, it's sometimes quite easy to still see where a cell is moving. So I think a unit is probably too much, also in terms of computational power you in the end need for doing the tracking. Yeah, so this approach definitely I didn't think about so far, and as I said, I'm still in the exploration phase of which different approaches could be possible. So.
Thanks a lot. Maybe I'll ask one last question. So Franziska, you mentioned when you showed the chambers that there are different kinds of cells present.
Yeah.
So this is something which is also recognized by the unit, that do you output a cell type along with the segmentation, or how is it this classification done at the end?
So currently the classification is done by just the recognition of the different fluorescence channels. So you have GFP, TX-red, and so on, and each one is for one specific cell type. But of course, you could also think about using the phase contrast images and doing a classification of the cells of the phase contrast image. But the question is just where to apply the neural network in the end, probably.
Thank you very much, Franziska. Thanks a lot again.
Thank you.